And I'll hand it over to you, Felix.
Thanks, Dixon. Yeah, hey, welcome everyone. Really cool to see so many new faces here. So I'm quite happy about the poll results also. I saw a lot of PyTorch, a lot of weights and biases, which is exactly what we will do in this demo today. So let me quickly share my screen. So before we dive into it, I want to give a short overview over modeling tools and experiment trackers in general that we have in ZenML. So maybe some of you are new to ZenML or are coming and have already trained PyTorch models, TensorFlow models, and want to convert them into ZenML pipelines and are wondering how to get started. So here I am on the ZenML webpage, zenml.io/integrations. And if you filter by modeling tools here, you can see all the modeling tools that we currently support. So today's community hour will be focused on PyTorch. But if you're, for instance, having a TensorFlow model or a sklearn model or any of those, and you are wondering how to use them instead, the overall workflow will be quite similar, how to turn them into ML pipelines. And for specific code, you can always go on the respective page, then click on the GitHub link, which will open up an example that actually uses TensorFlow. And here, for instance, you could go to the TensorFlow trainer, and you will see this is how I can use a TensorFlow Keras model inside my ZenML steps. Now, also, if the modeling tool that you want to use is not in this list, so let's say maybe you want to use CatBoost or some other tool that is not in the list right now, also don't worry. It is actually much easier to add a modeling tool to ZenML than you might think. In that case, just reach out to us on Slack, and we will always be happy to help you figure that out and maybe make it a new ZenML integration. The other category that we will look to today is the experiment tracker. So here, ZenML currently supports TensorBoard, weights and biases, and MLflow. Exactly the responses that we saw also in the questionnaire. And here the same thing. If you would like to use a custom one or have any questions, then always free to reach out to us on Slack. So with that being said, today we will have a look at how we can use those experiment trackers with PyTorch and how we get started with PyTorch in the first place. So what we will do is we will go through the PyTorch tutorial. So this is the official quick start of PyTorch. And we will transform this one into a ZenML pipeline and add the experiment tracking tools to it that I just showed. So maybe before we go into that code, let's have a quick look at what this quick start is doing. So if you're not a PyTorch guy, also don't worry. I think a lot of the concepts are somewhat similar to other deep learning frameworks, and the overall workflow of how you go from no ZenML to ZenML is always quite similar. So in this quick start, what is happening is we are training a PyTorch neural network on the fashion MNIST dataset, which is some image classification dataset. And yeah, so here in the beginning, they define the datasets, fashion MNIST, which is built in PyTorch. Then they define some data loaders, which are later used to iterate over those datasets efficiently. Then they define the model they want to train, which is a neural network in this case, with 3 parameterized linear layers. And then they train this model on the dataset using cross-entropy classification loss and stochastic gradient descent optimization with a certain learning rate. And how that works exactly is then shown here. So here is the training step for one epoch. So here we first switch the model to training modes, then iterate over the training data, make a prediction with the model, compute the loss, perform backpropagation to update the weights of the model, and then print the loss and the accuracy at certain intervals. And the same is done for the test step, so or the test epoch in that case. So here also for every epoch, this test is called, which does the same thing. It switches the model to evaluation mode, iterates over the test data, and computes loss and accuracy and prints it out. And then they have a big loop here where basically for each epoch they call train and test. So they have 5 epochs, and for each epoch they simply call, train, and test. And then there's some more stuff here on the bottom, such as how to save models and how to load models. But in ZenML, you won't have to take care of this. So this is what ZenML automatically does for you. All your models that you train, all your data is automatically stored and tracked somewhere. So we don't have to worry about that. OK, so now let's turn this into a ZenML pipeline. For this, I will go here into tile modes. So now if we want to get started here and turn this into a ZenML pipeline, the first question we have to ask ourselves is how could we structure this code? So right now, basically all of this code is just laying in one big file. And what we would like to do is structure this into an ML pipeline that consists of several independent steps that we can later also ideally replace, maybe with other steps. So there are many ways how you could do that. Maybe one that I would propose here is that you could, for instance, have one step that loads all the data. So it would define the data and then builds the data loader and return it. One step to create the model, and another step to perform the training and evaluation. So in ZenML code, that would look like the pipeline we have here. So we would have a function, which is our pipeline that has 3 arguments, each of which is a step. And then we define how those steps work together. So we would use the first step to load the 2 data loaders, the second step to define the model, and then the third step to train this model on the respective training data and evaluate it on the test data. And all we have to do to define a pipeline in ZenML is to write a function like this, and then write this pipeline decorator of ZenML on top of it. And now we have already defined a ZenML pipeline. And now we just need to define the steps that will then be used to fill those steps defined in the pipeline. So starting with data loading, in this case, we just copy the definition of the data sets here, which are those. Same thing for data loaders. We would copy that to data loaders, those 2 lines. And then we wrap this whole code in a Python function that we call load data. And we define what are the outputs that this function is going to have and what's a data type, which is important. So ZenML can correctly store those artifacts for you. And again, we write a ZenML step decorator on top of it. And now this is a ZenML step. For the model definition, it's quite similar. So here we would also copy over the model definition. And then we just write a Python function that builds this model, returns it. And again, we write ZenML step on top of it. Now for the training and evaluation, here the train and test methods are already 2 functions. So we can basically copy them in as is. Here we have made some changes to make the loss prints a bit nicer than in the PyTorch example, but it's literally the same code. Just copy paste it in. And then for the main loop and for the loss function and the optimizer, we put all of that into a third function, which we call train test, which we also decorate again with a ZenML step. And here we do exactly this loop logic. So we define the loss function, we define the optimizer, and then we do the loop where we iterate over the 2 other functions, calling train and test in each epoch. And that's already it. So as you saw, the recipe is basically always the same. You take your code, you put it into a Python function, you write step on top of the function or pipeline on top of the function if you want to make a pipeline. And then all we have to do now is to connect it together. So now we say we want to use this pipeline. And here we tell ZenML which steps we want to use in it, which we can now run. So here we can see we are using a neural network with 3 parameterized layers. And this is now training the torch model for us. So the loss hopefully keeps going down and the accuracy going up. And while this is happening, we can also spin up the ZenML UI in the dashboard in the background here. So we can get a visual representation of what's going on. So now let me switch to full screen mode for this. Here I might need to log in again. So now we're in the ZenML dashboard where we have the pipeline running. So we can see here one pipeline and one run, which is going on right now. Here we can see our PyTorch experiment tracking pipeline, some metadata that is tracked for it. And then importantly, we can also here have a visual representation of the pipeline, which is quite neat. And if we switch back, let's see how far this one got in the meanwhile. So now it has finished. Now we should also be able to see that in the UI. And yeah, now you would have, this is already the first benefit you would have now of having this in a pipeline, that you have a nice visualization of it, and you can have some metadata of your artifacts, of your models that you trained, and a lot of things like that. So that's the first part of what we want to see today, how to turn your PyTorch model in a ZenML into a ZenML pipeline. I hope much easier than you maybe expected. And now what we will do is we will add experiment tracking with TensorBoard and weights and biases to it. So in practice, you would not need both TensorBoard and weights and biases. It's sort of redundant since they do the same things, but for demo purposes, we will show both of them here. In practice, probably TensorBoard, I think, is a very popular model, especially in research. I think it's very intuitive, very easy to set up. And a lot of people who are working in research in small teams or working alone like it a lot. But the shortcoming of TensorBoard is a bit that the collaborative aspect is not so easy. So usually once you start working on something in a team, that's where tools like weights and biases or MLflow typically make more sense. So in order to use weights and biases in particular, we have to add this into our ZenML stack. So short reminder what a ZenML stack is. A ZenML stack basically is a combination of your infrastructure, and by default, ZenML already sets one up for you, which defines an orchestrator, that is the component that runs your code, and an artifact store, which defines the component that automatically saves and tracks your code, saves and tracks your artifacts. And by default, this is stored locally, but you could also configure this to run, for instance, in a Kubernetes cluster, or to save your data in an S3 bucket, or wherever. And what we will do now is we will add an experiment tracker of weight and bias into that stack. So in order to do that, you need to know three things. One is the weights and bias entity, one the project, and one the API key. Maybe let's start with the first two, entity and project. So here I'm going into weights and biases. And in weights and biases, you can see we have a ZenML team, for instance, and this ZenML team has various projects, such as the demos project, which I would like to log to right now. And in that case, ZenML would be the entity, and demos the project, already what I have written here. And now for the weights and biases API key. This one is what you would usually get when you log in the first time with weights and biases on your computer. So this would prompt you to go to this URL here, and then you would have to paste in this API key. So you are logged in with weights and biases, and here you would have to do the same thing. So you just go to this website, take the token, and then paste it here. That's all you need to do for the setup. And I have already set this up as a secret in my local weights and biases, so that's maybe something for another time. And now I can register an experiment tracker of type weights and biases in my ZenML setup. So what I do here is I run one command, ZenML experiment tracker register, give it a name, say I want to use type weights and biases, and then I define those three properties that we have just mentioned. Then I create a new stack called weights and biases stack and activate the stack. So now also in the UI, we will now see if we refresh this. So here we will now have two stacks and four stack components. So we can see here the weights and biases stack with a weights and biases experiment tracker. So it looks like it all worked. And also now let's make sure that we are also using that one. So this is the information of our current experiment tracker, which is indeed the weights and biases one. And now we basically will rerun the pipeline. So first we will make a few modifications to it. Maybe starting with TensorBoard. In order to use TensorBoard, we will use the summary writer class that is contained in Torch itself. So this is similar to how you would use TensorBoard anywhere. We build the summary writer and we pass in a certain directory, which is exactly where the artifacts of ZenML are stored by default. So we store the logs into the same location. And then we simply pass this writer into both the training and the test steps. And then in the steps, we call TensorBoard writer.addScalar, which then logs this information into TensorBoard. So in this case, the test loss and the test accuracy, the same here for the training loss and the training accuracy. Now, in order to use weights and biases, the setup is a bit different. Here we would first need to modify this step decorator and tell it explicitly, this is the experiment tracker we want to use, the weights and biases tracker that we just have defined in our stack. And then we can, after we have done that, we can call any weights and biases method as we would do otherwise. And we don't need to call the weights and bias in it. This is already done for us under the hood. So here we can write .log, for instance, to log the hyperparameters. We can call watch model, which will log the gradients of the model even. And somewhere here, we will also log the tests, loss and accuracy, and training loss and accuracy. So that's how you add those two components into, or how you would need to change your codes to use those two experiment trackers. And now we can rerun this pipeline again with our new components, which will now automatically log all the experiments both to TensorBoard and to weights and biases. So maybe while this is going on, we can also, here we should now be able to see, if we refresh this and go to our weights and bias stack, here we can now also see the runs that are running on this specific stack that we just defined. So we can again see that training data loading, model definition has already finished. Just train test is still executing. So now let's quickly wait for this guy to finish before we can see what we can do with the information that's this produced. So this should be the last epoch. And now you can see it's writing all the data to weights and biases, which is giving us a link here. And also it is written to TensorBoard. So first we will now have a look at TensorBoard. For this, ZenML has this util function, visualize TensorBoard, where you just pass in the pipeline name, the step name, and then it automatically fetches the right logs for you. So we can start this up, and then we will see a TensorBoard visualization here. And this will show you, in this case, the curves for both the accuracy and losses. And this is super useful in practice, right? Because now we can actually use this information to improve our model. So for instance, in this case, if we look at those curves, we could see, first of all, if we look at the values, that we achieved a training accuracy of around 65% and a test accuracy also of around 65%, meaning that we don't have an overfitting problem since our test and training accuracy are almost the same. Another thing we could see here is that the training accuracy is more or less converged. So training this for longer probably would also not make the model much better. And then from this information, we could, for instance, in this case here, quite quickly tell that in order to improve the model or the final test accuracy, we would need to make the model a bit stronger, maybe by adding some more layers or by adding some more neurons in one of the layers, which is very powerful information, right? Just from two simple graphs that you can get this easily. And that's why everyone in research also is using some sort of experiment tracking tool to get better models. Now, similarly, okay, this opened in the wrong window now for me, unfortunately. Let's try again. Okay, let me quickly drag this over. Similarly, we can see all of this in weights and biases now. So here we have our current run. We have all the curves. We even have the gradients of the model, which you can use to debug if your model goes wrong. And another part of why experiment trackers are very useful is that we now have a table view here where we can see for each of the models that we trained, what was the test accuracy, what were the hyperparameters that we used. So if you train a lot of models, this really helps you to find out, first of all, how did I produce the best model that I had so far, and also how do certain hyperparameters affect my models. And for instance, here in weights and biases, this is a collaborative tool. So if one of my colleagues would now run some experiments, and at some point I need to reproduce them, and maybe that colleague is on vacation, I could quite quickly see here what are the hyperparameters that he used. And with ZenML, I could find out what the code was that he used and what the data was that he used, and then I can quite easily reproduce the exact model that he trained, which is the real power of those experiment tracking tools and of general metadata tracking tools like ZenML. So yeah, that's it for this presentation. I see we're also quite close to the time limit, but I would still like to keep it open maybe for a few questions in case there are some questions from the community. Yeah, so if anyone has questions on experiment tracking, PyTorch, or anything, maybe also debugging errors as we saw in the beginning, then yeah, please raise your voice. And perhaps we should also turn off recording now, right?
Yes, I'm doing that.